Hello students. In this video lecture we are going to discuss about minimum spanning tree. First, what is a minimum spanning tree? A minimum spanning tree is a subgraph of a given graph such that it is acyclic and also it's well connected. So what do we mean by acyclic subgraph is that we must get rid of all the cycles from a graph. Remember that a graph is allowed to have cycles. Unlike a tree, a graph may or may not have cycles. So which are redundant connections. But if you want to create a minimum spanning tree, then we must eliminate all the cycles from the graph. If you remove the cycles, then it can also be treated as a tree. That's why we are looking at the title as minimum spanning tree instead of minimum spanning graph. If such a graph has weights assigned to its edges, a minimum spanning tree is its spanning tree of the smallest weight, where the weight of a tree is defined as the sum of weights of all its edges. So we have already seen that a graph may be weighted or not weighted. So if a graph is weighted, which that means that every edge on the graph is given a value, and if you create a minimum spanning tree out of a weighted graph, and if you find the sum of the weights of all the edges, it must be the minimum sum that you could produce out of that particular graph. The actual graph will have much higher weight, and reducing it to a minimum spanning tree will result in the minimum possible sum such that the tree is still connected. This particular the algorithm is concept data structure is very useful while we want to construct the interconnections of communication networks, so that you can estimate what is the minimum distance that needs to be covered in order to connect various points. Let's say a network company want to interconnect the cities in the here in the state of Tamil Nadu. So they want to find out what is the minimum distance they need to cover so that they can reduce the overall cost of the communication. So in such case, they may the original state is a graph, because there are cycles. For example, from Tanjavur to Trichy, there are many paths. So different paths exist for going from Tanjavur to Trichy. But you don't need to interconnect all the paths in order to connect the Tanjavur city, Trichy. You can choose one of the paths that are available between the two cities, so that the total cost of the cable is reduced. So minimum spanning tree has got application in a number of domains. So this is an example for understanding what do you mean by a minimum spanning tree. This is a graph. Given graph is having A, B, C and D, and you can see there is a cycle which interconnects A, D and C. So if I want to go from A to D, I can either use this particular path or I can use this path. So there is a redundant path available. Now if I create a minimum spanning tree or a subgraph of the given graph without any cycle, then there are three possibilities. This is one, this is the second, and the third one is given like this. And out of this, if you want to identify the minimum spanning tree, the one that produces the lowest sum, it's actually the second one. The second subgraph is producing the lowest sum, because 3 to 1, which results in 6, whereas the other two, though they are spanning trees, but they are not the minimum one. So this is an example of a minimum spanning tree. So we have eliminated the cycle, and still ensured that every vertex is connected with every other vertex, and also the overall cost of the sum of the edges is minimum. Now we need to find an algorithmic way of getting this result. So we have to now get into the algorithms used for constructing the minimum spanning tree. There are two algorithms available. The first one is called the Prim's algorithm. The idea of a Prim's algorithm is that it keeps expanding the subtrees. So it starts from one vertex, it will add one vertex into the new graph or the subgraph which is going to be constructed, and then it will expand that by adding another vertex, and then it will keep on adding vertices and edges. Finally it should have got all the vertices and inside the minimum spanning tree, but not necessarily all the edges. So some of the edges may be dropped because they may be forming a cycle, but all the vertices have to be included into the resultant graph. Only then it can be treated as a connected graph. And it follows the greedy approach in the sense it keeps attaching the smallest, it always looks for the best option, so that that can be included into the solution. So in this way, in each iteration it will add one new vertex which is the minimum in the among the given choices, and the algorithm stops after all the graph's vertices have been included into the tree being constructed. I'll show you a demo of this algorithm, and it will be easier. uh, so before looking at the algorithm, let me take you to the example. So there is a graph which you can see is given with these vertices and the edges, and it's a weighted graph. Each edge has got a unique value. Now we need to construct a minimum spanning tree, and you can clearly see there are number of cycles. So here there is a cycle, and there is another cycle here. So we need to get rid of all the cycles, and we have to apply the Prim's algorithm for getting the result. Step 1, you have to include one of the vertices into the graph. Remember that for unlike a tree, there is no starting point for a graph. There is no root available for a graph. So we can commence the insertion from any vertex of our choice. But conventionally, we will go by the alphabetical order, or if it is if there are numbers, then in ascending order. So I'm including A into the minimum spanning tree that is going to be constructed. Next, we have to now choose an adjacent vertex from A which has the lowest weight. But for A there is only one choice, so it has got only one choice available, which is A to X. So we just have to include it. And before that, this list will comprise of all the vertices that have already been included into the minimum spanning tree, so that we don't by mistake add one more edge for that particular vertex. Now X is included into the minimum spanning tree, and that is also added into the list. Now we have got two choices, that is A and X. So we now have to choose the next vertex which is adjacent to either X or A, but having the minimum weight. Again, we don't have much choice. We actually have two choices now. From X there is an edge from edge to H, and there is another edge to G. But comparing their weights, we are going to choose the edge from X to H. So that is included. It's also added into the list. Now we have got three vertices into this list. So now we can choose any one of the vertices which are either adjacent to A, X or H, but with the minimum weight. So from X we have already included H. The other vertex that is or other edge is having weight 3. Whereas from H we have got a edge to E which is having 2, which must be the lowest in the given set of choices. So we have to include that edge into the minimum spanning tree, and once again we have to repeat that process. So we have now got 4 vertices into this. Okay, we have to now include it. Okay, 4 vertices, and so we can include any vertex which is adjacent to any one of these 4 vertices, but the one with the minimum weight. So considering the choices, we have got E to M with 3 and X to G also with 3. But going by the order, let us include X to G. Though both are equal, we have started with from A, and so the adjacency matrix would have got this order: A, X, G, H, P, and so on. So in that order if you go, then X to G will be included next. Next we have got G to P, which is having the weight of 3, so that is included. Next we can include either P to H, which is weight 5, or E to M, which is 3, or E to Y, which is 4. But going by the lowest weight, E to M is the next best candidate, so that is included. And next edge would be M to J, so it's having only 2, so it must be the next edge to be included. And finally M to Y. So with this we have included all the edges. This algorithm will end as soon as you have got all the edges in all the vertices into the resultant list. So that means that we have covered all the vertices, and we have also avoided the cycle. So this edge has been I mean, you can see clearly that both the edges which formed the cycles have been automatically eliminated from the resultant minimum spanning tree. So this is the result of the Prim's algorithm. Hope you could have you could understand the implementation of the Prim's algorithm. So the idea is very simple. You start with one vertex, include into the resultant minimum spanning tree, and you keep choosing the next vertex which is adjacent of any one of the already included vertex of the list, and it has to have the lowest weight. In that way, if you follow, you will construct the minimum spanning tree naturally, and as soon as you have got all the vertices in this list, you must immediately stop the algorithm, and you have to now display the result, which is the minimum spanning tree according to Prim's algorithm. If you now look at the algorithm which is given in the previous slide, so for what is happening here is that VT, the set of vertices that are initialized with any vertex. So you are choosing V0 as the first vertex to start from, and then you have to find the minimum edge between the chosen wedge, which is V and V0 and any other edge, such that V is in Vt and U is in V minus Vt. That is, you have to choose an edge vertex which is adjacent to one of the vertices that are already included into the list. So and also the new vertex is not already part of the list. So if such a vertex is found, then include it into the list of vertices that you are accumulating, and also include that edge also into the list. So if you follow this for the number of times v minus 1 times, at the end of it you would have got the minimum spanning tree that we had produced here. And this example I just leave it to your own practice. You can just follow the same procedure we followed here and try to construct the minimum spanning tree according to Prim's algorithm. Remember that we have got two algorithms, both will produce the same results, except in few rare cases. The result of Prim's algorithm as well as the Kruskal algorithm, which we are going to discuss now, will be same. So it's not just the result that is needed for you to get your marks. You must also provide the step by step procedure, just like I showed you the demo, that in the first step I added A, next step I added X, next I added H. So these steps have to be clearly listed out. Only then it will be considered as a correct result. But if you go to the Kruskal algorithm, the final result will be equivalent to this one, but the steps will be different. So you must show that difference clearly when you answer this question. and this is the actual algorithm given in the textbook. So what is happening here is that it is just expanded version of the same algorithm. So it starts loops through all the vertices. So you have to start this loop in order to commence the construction of the minimum spanning tree, and in each vertex you must choose an vertex and check whether its out degree is greater than 0, which means whether it has got any vertex that is adjacent to it. If so, then you go into the next loop through all edges which are adjacent to the chosen vertex, and if that particular vertex is not already in the tree, which is minimum spanning tree, then it's a potential candidate, because you need to choose new vertices which are already not part of the tree. So if the destination not in the tree, then you set in tree flag to false, and if then you compare whether its weight is less than the minimum edge. So you have to keep updating the minimum edge value according to the new minimum. So if the new edge weight is lower than the minimum edge, then you update it. So this is that is done in the next two steps. You change the minimum edge to the weight of the new edge, and also you change the edge to the new edge. So in this way, if you run this loop, at the end of the loop you would have got the lowest weight in this variable, and also the edge in the min edge, and now you just have to include that edge into the minimum spanning tree. So that is done in the next case. If minimum edge location not null, then it's getting included into the resultant minimum spanning tree. Okay, now we are going to look at the next algorithm called Kruskal algorithm. Kruskal's algorithm is also meant for producing the minimum spanning tree, but its procedure is slightly different. This was invented by a person called Joseph Kruskal, who discovered this algorithm when he was doing his second year graduate student. This has been underlined because to remind you that you are also in your second year, so you have very well the chance of becoming another Kruskal by writing your own algorithm for some problem. So let's hope that one of you become a Kruskal in future. So in this case, what happens is that the difference between Kruskal and Prim's is just in the last line. So as for the Kruskal algorithm, uh, not necessarily connected on intermediate stages of the algorithm. So what is the difference is that in the Prim's algorithm, you can recall that uh, you have to construct the minimum spanning tree such that it is always interconnected. So the all the vertices that you are adding to the new minimum spanning tree, they remain interconnected with the minimum spanning tree. Like say for example, A and X are connected, X and H are also connected, H and E also connected. So it continues to remain connected until the last step. But this is not necessary in the case of Kruskal algorithm. So in the intermediate steps, the edges may be not connected, they can be separated, but final minimum spanning tree should be interconnected. So I will show you the demo, you will clearly understand this particular point. So let's take the same example. Now what happened to understand the difference between the steps? What happens is that first this is what the difference. So what you have to do in the case of Kruskal is that you have to straight away choose the edge with the lowest value, which means I have got many vertices or many edges having weight of 2, but going by the order X to H is the first edge which has the weight of 2. So that is included into the graph. Then in Prim's algorithm, you have to include the next vertex which is adjacent with either X or H. That is a restriction. But here no such restriction. I can choose any edge irrespective of whether it is interconnected with H or X. But in the given example, we actually choose the E because it's having the weight of 2. If for example if this was not 2, let's say some higher value, then I would have gone for the M to J. Even though it is not at all interconnected, it does not matter, I can still include it into the minimum spanning tree. That is the difference of Kruskal algorithm. So because of the lowest value I have included H to E, and next I'm going to include M to J because of the value, and then I have to include X to G with the value of 3, next G to P, and then E to M, next M to Y. So once again we have produced the same minimum spanning tree, but in the steps were slightly different. So you would have understood the difference between Prim's and Kruskal algorithm. So this is the algorithm given for the Kruskal. So what you have to do is that you just have to keep constructing the minimum spanning tree. Only condition is that when you want to include a new edge into the minimum spanning tree, you just have to check whether adding that will not form a cycle. That is, the minimum spanning tree should remain acyclic. That is the only criteria you have to check. Unlike the Prim's algorithm, where you have to check whether the new edge is adjacent with the, one of the vertices that are already into the list. That is not at all that you don't need to check for that condition here. You only have to check whether adding the new edge into the minimum spanning tree won't form any cycle. If so, you can just add it into the minimum spanning tree. I do have another example, so let's try this also. So which one is having the lowest edge? B to C, so it's included. Next lowest is D to E, and then we have got A to C, I think. So A to C is included. After that C to D, and then D to F. So we have covered all the vertices. So we have included all the vertices into the minimum spanning tree, and that is what the net result of this minimum spanning tree. So these two algorithms are used widely for constructing the minimum spanning tree, and it's very important that you know the subtle difference between the implementation of the two algorithms.